So, good morning, students. We will continue the previous lecture, and if I'm right, this is where we have stopped the previous lecture, and we were discussing about the how to handle the spin splitting pattern in the carbon 13 NMR spectroscopy, especially. The spin coupling is mainly seen from the 13 carbon and which is connected with a proton, and these coupling constants are really high, and therefore as a result we find it very difficult to interpret the spectrum because of they occupy much larger space in the spectrum. Therefore each peak appears like a individual peak. So if you are a beginner, it becomes more even cumbersome now. Therefore, there are a few techniques have been developed, and those techniques are primarily called as a decoupling technique or double resonance NMR technique. And these really help us to simplify the spectrum in the carbon 13 NMR spectrum. So based on the requirement, there are different techniques, and one technique that I have explained in the previous class is this broadband decoupling. In the broadband decoupling, here what we do, we use radio frequency, a band of width, roughly about 40 to 70 megahertz frequency, and then we apply, and as a result of which all the proton signals will be saturated, and then we don't see any coupling. Okay, and then we only see peaks correspond to the carbons, whether it is a primary carbon, secondary carbon, or tertiary or quaternary carbon. We will see all those signals in the spectrum. Okay, so this is really helpful to confirm certain aspect with regard to the molecular structure of a compound, which is already proven in the proton NMR spectroscopy. On the other hand, since you are losing some of the information, coupling information, therefore, if you are really dealing with the unknown compounds, so this coupling is, in fact, it is needed, because only when you see the coupling pattern, whether it is a triplet or doublet or quartet, you will be able to judge whether it is how many neighbors it is having, a particular nucleus having, a particular carbon nucleus is having. Therefore, the advantage, and both advantages are there with the broadband decoupling technique, and based on your requirement. And suppose if we have already confirmed the molecular structure by using some other, let's say the proton NMR spectroscopy, and then if you want to just confirm further, then probably you can use this broadband decoupling just to say that C13 NMR are also matching with the expected carbon 13 nuclei present in the molecule. That's the information that you can say, but more than that you can't say. So the other technique actually is the off resonance decoupling technique, and as the name suggests, in this technique we use a radio frequency frequency which is which is matching, which is slightly away from the either downfielded or upfielded frequency to that of a proton resonance signal. What I mean is that, let's say that to record this one, to have the off resonance decoupling technique, first of all, we need to record the proton NMR spectrum of the same compound and look at the proton signals. Let's say if some proton is resonating at 2 ppm, then in this off resonance decoupling technique, to get the NMR spectrum with little bit of splitting, then what we do, we use a radio frequency generator whose frequency matches with the 2 ppm, not exactly 2 ppm, maybe 1.7 ppm or maybe 2.3 ppm. So it is not exactly at the resonating frequency of the proton. So if you use the pulse, radio frequency pulse in such a manner, then what happens? The coupling constant actually minimized. They will not be vanished. Unlike the previous case about when the decoupling, the coupling constants are still remain, but then they will be reduced to a greater extent. Therefore, the splitting pattern retains, and then we will have a much more clarity whether it is a splitted peak or the a separate peak. That the information we'll get from the operations technique. Therefore, again, in the same this technique also, it has advantage as well as disadvantage. Since the coupling is not totally eliminated, then it is a disadvantage. When it is a disadvantage, if you want to just to confirm the how many carbons are there at that time, by looking at the splitting, you may think that this is a new peak. Otherwise, this is okay. Suppose if you are dealing with unknown compound, and most of the case that is the case, we deal with a lot of molecules in a day-to-day basis, and these molecular structure need to be confirmed and characterized time to time. So in those situations, since we don't know what exactly is the neighbor of a particular carbon, this half resonance will help you to resolve that problem. Okay, so let me explain with an example. As you can see on the left-hand side, sorry, this is the comparative NMR spectrum of ethyl benzene. Okay, and the top upper layer, you can see this is the proton NMR spectrum of ethyl benzene. So this is the proton NMR spectrum of ethyl benzene, and aromatic protons are not shown here. So this is the point I just want to tell you. Okay. The second thing is that okay, we know from this spectrum by recording the proton NMR spectrum, I know that where exactly protons are resonating. Now the decoupler frequency is set that not exactly on the resonating frequency, but slightly away from the resonating frequency. As you can see here, in this case, the C13 NMR spectra are recorded by the decoupler frequency using the decoupler frequency at this frequency, minus 0.2. Okay, at that frequency, the resonating frequency. I mean, this is a delta in ppm. Please remember that the x-axis is the ppm scale, delta scale, but it is nothing but the frequency. So this is basically the shift in from the standard or reference, right? The x-axis is the reference is basically x-axis is the frequency, and it is measured the shift, how much with respect to a particular frequency, how much a proton signal is shifted away from that one. We are measuring the number spectroscopy, right? So it is essentially, even though we are speaking about the delta ppm, 1 ppm, 2 ppm, this x scale is in fact it is a frequency scale, right? Okay, we normalized with the resonating frequency of the operating spectrometer. That's how it becomes the ppm scale. But it is a frequency, right? So I choose anywhere, this place. I can choose. It's my choice, but I have to choose a frequency whose frequency is not matching exactly. These are the resonating frequency. Since there is a resonance, that's what we see a quartet here, and then that's what we see a triplet here. So we have to choose anything. So this particular case example, they have chosen this minus 0.2 is the operating the decoupler frequency to record the off resonance spectrum of ethyl benzene. So this is off resonance. It is not exactly on resonance. It is off resonance, right? And then this spectrum is the coupled spectra of the same ethyl benzene. So this is the C13 NMR spectra, in fact, okay, C13 NMR spectra of the same ethyl benzene, but it is not a decoupled, it is a coupled spectrum. Okay, coupling is there. Okay, therefore, that is what, we decided to go for the decoupling techniques, right? You can see here there is a triplet. There is a one peak, there is a one peak, there is another peak. There are 3 peaks. And then here there is a small spike, and then there is some intense 2 lines are there, and then here you can see another one. So this is the problem that we want to eliminate, right, in our carbon 13 NMR. Okay, so this is a coupled spectra. This particular spectrum is a coupled spectra, and this bottom one you can see here. I'm sorry. Bottom one you can see here. The bottom one is a decoupled, totally decoupled. That is the broadband decoupled spectra. What happens exactly when we follow that broadband decoupling? The total splitting is ruled out. So there won't be any splitting. If you have one carbon and the carbon doesn't interact with the proton because we use the frequency of that proton and all the a broad band of resonating frequency as a decoupler. Therefore, all the proton interaction with the carbon will be eliminated. Therefore, we see only the signal for that particular carbon. Okay, that is the spectrum, and this is the coupled spectrum. And this is what exactly the middle one is the off resonant spectrum. You can see, the coupling here. The coupling is so much, right? This much is the coupling. Okay, here the coupling retained with a less coupling constant. Therefore, this is really good. Coupling means why we need a coupling. Coupling information is very much important. How many neighbors are there? If it is a triplet, a particular signal is triplet, that means it is seeing a two neighbors, two different neighbors. That is the information that is required while solving the puzzle of molecular structure. Okay, so this is the advantage. Similarly, this quartet you can see here, the same quartet here, it is minimized and then nicely it is resolved, and then it occupies a very small place with a nice signal to noise ratio also enhances. Okay, so this is the broad explanation, a brief explanation about the off resonance technique. So apart from the off resonance, these two techniques, there are several techniques, and we don't have really time to discuss all those things. And moreover, those are not important at the MSc level. But you can always read the standard textbook that you can get it. And then different other techniques are also there. Other than these two techniques, I'm going to discuss something which is very important, and I have seen a couple of questions are coming from that particular technique, that is the DEPT. And before that, let me show you one more example. This is the NN-diethyl benzaldehyde. Okay, NN-diethyl benzaldehyde, and both off resonance and broadband decoupling spectra are shown here. Can anybody say which one is the broadband decoupling spectrum? Upper one or down one? Can anybody say which one is the decoupled spectrum, broadband decoupled, and which one is the off resonance decoupled spectrum? Hello? 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 Are you there?
Yes, sir.
Why nobody is talking? Can you hear my voice or not?
Yes, sir, I can hear.
Yeah. Nobody is talking. What happened? Bhuvaneshwaran. Let me say hi to everybody. I think that's how I should make you involved in the class. Huh? Ashna.
Yes, sir.
Oh, I'm asking something. Why don't you switch on mic and then say yes or no? Anyway, I'm not going to beat you, right? I'm not going to scold you also. Maximum I will scold you, sorry. Maximum I will scold you. Nothing will happen. Na? Surya? Surya?
Yes, sir.
Why you are not talking when I'm asking question? Always Kuntal is coming and talking something. Other than Kuntal, nobody, sometimes Ravi also. Why you people are not responding when I'm asking some question? Is there any difficulty? Huh? Tell me. I don't see even your face also. I'm just talking to you my desktop, my screen of a laptop. That's all. Huh? Srileka, are you there?
Yes, sir.
Okay. Swapna?
Yes, sir.
Okay. You guys have to respond. Okay. Otherwise, I feel like not only myself, who are teaching and they are asking some question. This is the difficulty in the online lecture. Okay. A teacher cannot teach properly, cannot imagine a class without the physical presence of a students or the audience. Now, my difficulty, I know, of course, you do have the problem. You don't see my face and you don't see my gestures. You don't see my explanation properly. Of course, I think you may see a little bit of my face, but then there will be always a delay. I'm very much sure there will be always a delay from my voice and my picture what you see in the screen because of the poor internet. So therefore, when I ask something, you have your own problems. I'm not denying. I have my own problems. But just to have a little bit of interaction, sometimes I'm asking some questions. At that time, you guys have to respond. Otherwise, I feel like I am teaching to some liveless object. Okay. In fact, that is true. I'm teaching to the laptop screen, not to you. That's what I feel always. I don't feel really I'm teaching to students. Okay, fine. So when I ask you, please respond and tell whether you know the answer or not. Okay, that should be the way. Okay, fine. Let me go back. I'm showing the two spectrum. I'm showing the off resonance as well as the decoupled spectra of diethyl and diethyl benzaldehyde. I asked a question, which one is the broadband decoupled spectrum, which one is the off resonance decoupled spectrum. Obviously, the upper one is the off resonance decoupled spectrum because you can see a splitting, right? This one is the broadband decoupling, right? Because there is no coupling and all signals are singulated. They appear like a singlet. Therefore, we can easily come to a conclusion that this is the bottom one is the broadband decoupled spectrum, the upper one is the off resonance decoupled spectrum. Okay, fine. So the third one I have taken up. Usually those are the two things that we use it, but this is a special technique which is really given a little bit of importance in this CSR in a recent question paper. So therefore, I had taken up this technique also to explain briefly. Again, I am not really interested to explain all the what are the different physical concept behind this distortionless enhancement by polarization transfer. In a shorthand notation, it is a DEPT technique. This is again mostly it is given in carbon nuclei, but then it is not the case that it is only used for carbon 13, but it can be used for the other nuclei also. Okay, so this is also very important technique to distinguish and to differentiate the primary carbons, secondary carbons, tertiary carbons, and then quaternary carbons. So these things are really, this particular technique is really helpful to differentiate one from the other. Okay, and this question has been asked many times. These years are also in the recent question paper. When you go through it, you will understand. Therefore, I'm going to discuss the essence of this particular technique, not the physical concept behind it. Okay, um, because that is what important while solving the question papers. Therefore, I will confine my discussion only to that. So this particular technique, already I have given a little bit of a little bit of explanation that this is really useful. In the simple C13 NMR spectrum spectroscopy, we get a carbon 13 spectrum irrespective of all the carbons, whether they are primary, secondary, tertiary, or quaternary. So all the carbons will give the NMR signals. Okay, and then those signals will be there. But there are many instances where if you want to know what is the real the interaction, what type of carbon it is, that kind of information we don't get really from the C13. Okay, whether it is a tertiary or carbon or a primary carbon or quaternary, this information we don't get from the C13. I showed you a couple of C13 NMR spectra of ethyl benzene I showed you, and diethyl thing also I have showed you. So all the carbons will give spectra, signals. Okay, but this one is a special in the sense that it will differentiate one from the others. Okay, and I must tell you here, it is not a simple technique like a C13 NMR spectrum. Okay, I must tell you, this is also true, that in a one single scan, that you will not be able to get the information. You will not be able to differentiate primary carbon from the secondary, or secondary carbon from the tertiary. So this kind of differentiation you will not be able to do. In fact, it is the combination of 4 scans, which is not a one scan. It is like a 4 scans are actually usually done under this particular experimental technique. Okay, so this diagram, what you see on the slide, is basically explains you what is the pulse basic differences in terms of pulses used in NMR spectroscopy to record a simple C13. These are the pulse sequence generally used. Okay, we use a 90-degree pulse, and then we use then later on there is another we give some delay, and then we give 180, and then we start acquiescing the signal. Okay, that is the FID. So FID will generate. So this, what you see here, is a FID, and this FID, if you process, then you will get the signal. Okay, all the carbon will be seen. But in addition to this, in a decoupler technique, especially under the DEPT technique, we use different pulses. Okay, apart from the general 90-degree and 80-degree pulse, we also use different pulses. Okay, different pulses we use. I must tell you, this is a 45-degree pulse, 90-degree pulse, 135-degree pulse. What are those exactly? And please remember that when I explained maybe in the at the beginning of NMR lectures, I have given a couple of points about what is 90-degree pulse. Okay, so in the pulse technique, older days, I told you that this is basically scanning one by one. Okay, either field sweep or frequency sweep method we follow. Okay, keeping the magnetic field constant, we vary the frequency of the resonating RF pulse. Therefore, the RF generator. Therefore, the nuclear comes under resonating. On the other hand, you can do vice versa also. That you can keep the resonating frequency fixed, and then vary the magnetic field of the spectrometer. Therefore, the nuclei present in a given molecule come and resonate. Therefore, you will see signals. Those are the old technique, but later on it was modified, and then we switched over to the pulse NMR technique. In the pulse NMR technique, they use a branch of frequency rather than a one frequency at a time. Okay, and I have given explanation like the piano. So let's say you are playing a piano, and the scanning can be just take an example of piano, and the piano, if you want to record the sounds of that piano key coming from the piano keys, and that is let's say that is the task. And how do you do that? So one way is that if I given a task, I will press one, I will record that thing. Okay, and then with my ear I will record it and note down. Then next second key I will press it, and then I will record third key, fourth key, etc. And all the 64 keys I will be pressing, and then I will be recording the sounds. That is one way which we actually can correlate with the simple old scanning methods, field sweep or frequency method. Okay, but later on, the same example I have given you, like if you want to record, if you want to cut short the time, what you can do, you just slash the piano from one side with a rod or with anything, with your finger, you just slash it. Okay, then the recording is over. Okay, just a slash all the 64 keys, just 1 second. Maximum it will take 1 second to slash it. Once you slash it, then all the sounds came out at once. Okay, and then now to differentiate those scans, we use some different techniques and then to resolve it. Okay, so how much time you are applying this thing, it depends upon what kind of radio frequency pulse and how much time that you are giving those frequency. Based on that, your net magnetization vector actually will come and resonate in different angle. Okay, and okay, so that is the pulse technique. And then the 45 degree, 90 degree, 180 degree terminology came into the picture because of the net magnetization vector and its orientation in the plane with respect to the applied magnetic field. When you apply a 90 degree pulse, that will resonate in the XY plane. 40 degree means that initially it was here, then it will tip 45 degree from the Z axis, okay? And then it will somewhere here, it will be resonating in this manner, okay? But if it is 90 and this plane, it will resonate. Okay, so that is what exactly meaning of the pulses is, okay? They represent actually the 90 degree, 40 degree, 135 degree, they represent where the net magnetization vector is resonating. Okay, please remember that. But essentially, in principle, these are nothing but how much time you are applying, how much time this frequency, which I am talking about, you are applying. That is actually the meaning. But when you talk about the NMR technicalities, we only speak in terms of the angles. Okay, so please remember that. But actually, in reality, how much time you are applying, based on that, your magnetization vector will resonate in a particular with respect to z-axis, and then it will relax back. When it is relaxing back, and then it will generate signals, and that's what the NMR signal is. Okay, so that's the backdrop of all these 45, 90, and then 135. I'm sure that you can go back if you want further details. So what I'm trying to say is that the DEPT technique is slightly different than the carbon-13 element. In which way it is different, I'm trying to explain, and this is the pulse sequence we use it, the simple carbon-13 NMR, which gives all the carbon signal irrespective of primary, secondary, tertiary, and quaternary carbons. Whereas in the case of DEPT technique, we use a different pulse, different decouplers we apply. And those typical things are like 45, 90, and then 135 decouplers. Okay, the pulses we use as through the decoupler. Therefore, we get some more information. What is the information that we get? Let's see that. Let's try to understand an example. So this is the palette. Okay, and in this spectrum, in this technique. You can see the bottom one is the simple carbon-13 NMR spectrum of this compound. Okay. Okay. So this is the. So this is the C13 NMR spectrum of the diethyl phthalate. And then the DEPT technique, as I mentioned, that we apply different pulses and we record the spectrum. The one is 45 degree pulse, the second one is the 90 degree pulse, and then third one is the 130. So there are 3 different pulses we are using. Suppose if we use the 45 degree pulse, okay, 45 degree pulse, please note down, 45 degree pulse will give you the primary carbon signals, secondary carbon signals, and tertiary carbon signals. That means primary means CH3 signals. CH3, right? That signal we will obtain. Similarly, we will also get secondary, that is CH2, and tertiary, that is CH. So these are 3 signals we can see. Okay, that is a point number 1. The point number 2, when you apply the 90 degree pulse, in the DEPT 90 degree pulse, then what we get is only the tertiary carbons. Only the tertiary carbons. Please remember, and note down. In the final scan, we give 130 degree pulse. We give 130 degree pulse, and then we try to record the carbon-13. This gives all the CH proton, that means that the tertiary protons and the primary protons will give you a positive signal, while the Secondary carbons will give you a negative signal. I repeat the same thing. The primary and the tertiary carbon signals will be found positive in the depth 135 scan, and in the case of a secondary carbon, it will be a negative signal will be seen. Okay, and then let us now having with these 3 points, let's try to understand this with this example. Diethyl phthalate, this is the spectrum. So you can see here. This is a methyl. Methyl is a primary. This is a secondary, and this is a tertiary. Sorry, this is a quaternary. Right? There are no any other things. Right? So everything is connected. 4 bonds are there. This is we consider as a quaternary, and this one is again a quaternary. Right? This one is also quaternary. This one is also quaternary. So these 4 carbons are there, which we call it as a quaternary signals, and these 4 signals will be absent. Okay, when you record the point, you please remember that when you apply that, when you do the DEPT scan 45, DEPT 45 scan, the quaternary signals will be totally gone, and you don't see that. That is exactly is the case. You can see here that the zero signal, carbonyl stretching signal in a simple carbon 39 spectrum, they will be seen from 160 to 220, anywhere that you can find, depending upon the chemical environment. Right? So those signals in the depth 45 scan totally missed out. So point number 1. And then when you go to depth 90-degree scan, okay, 90-degree scan, the secondary, you don't find anything. Okay, there is no other signal except these 2. Okay, you have 4 signals here in the 45 scan. Okay, these are all maybe a primary, secondary, or tertiary. We don't know what it is. Okay, quaternary is totally absent. When it comes to the 90, according to the point which I mentioned, this will give you only the tertiary. This will give you only the tertiary. So here only these 2 signals are present, right? Therefore, you can confirm these are the tertiary, and the other 2 signals you can interpret to either primary or secondary. Okay, these 2 things can be interpreted to primary or secondary. Now, when you scan with the 135-degree pulse in the same depth experiment, what will happen that these 2 signals again present, and then all the 3 signals are there. I mean, the primary, secondary, tertiary, all signals are there, but primary and tertiary is positive, right? These are the positive, and the CH2 signal is found to be negative. So this is the difference. So therefore, you can confirm this as a secondary signal because this is negative, right? So this is how basically we try to assign the carbon signal, and therefore we will try to arrive at the appropriate molecular structure of the compound, which is under being studied. Okay, so this is a good technique. And the questions are asked in the, of course, this is the same explanation what I have explained to you. So there is nothing much. The questions are asked in the CSR point of view in this manner. They are giving, menthol. They are giving some kind of compound. Okay, and then they are telling that what kind of signal you will find, how many signals you will find. Okay, and that information, if you want to answer this information, that you should know. Depth 45-degree scan, that you will get only primary, secondary, tertiary. Then 90-degree, tertiary only will be obtained. And depth 135, like depth 45 scan, you get all the primary, secondary, tertiary, but there is a difference. The secondary carbon signals will be negative, while the primary and the tertiary will be positive. So that's the difference, and that's the point to be noted, so that you can interpret any of the molecular structure. Okay, so that's all about this thing, and further details, maybe fine details, how this is physically done, why this is happening. This is actually totally beyond the scope of this course. Therefore, I will not go to those details. Okay. Right. With this, I will stop my discussion on carbon-13 NMR, and then I will go to other topic of our discussion today, that is the nuclear overhazard effect. Okay, no, nuclear overhazard effect is another important technique which really gives us a lot of information, especially when you are dealing with the natural products and some of the total synthesis, drug molecule, which are very complicated drug molecule. Let's say, for example, Taxol molecule, which you are trying to understand the stereochemistry. So this NOE techniques, NOE principle is being used, and there are several 2D NMR techniques are developed based on the nuclear overhazard effect. Okay, NOE means nuclear overhazard effect, and Overhauser is a scientist, and in 1953, what he found is this. Okay, so this name actually came from his discovery. He found something in the case of electron spin resonance. So what he found is that when he is trying to saturate the electron resonance in a paramagnetic system, he found that there is a difference in intensity, resonance intensity of a nuclei, which is connected with that. Okay, so he is a person, he was trying to work on the EPS spectroscopy. What he observed was actually the electron when it is saturated, the electron resonance when it is saturated, the nuclear resonance is intensity getting either increased or decreased. That is the effect that he has observed for the first time in 1953. And this effect later on was systematically suggested as studied by several people, and then in fact it is applied to various other fields that I will give you a brief details as I proceed further. And initially the observation was only between a nuclei and electron. So electron resonance, when you are trying to saturate a nucleus, intensity is getting or increased or decreased. That is observation. But later on it was found this is also true in the case of nuclear magnetic resonance, where two nuclei are there. Suppose if you have two nuclei, and one of the nuclei, if you try to saturate, then other nucleus resonance intensity either goes up or down. Either it will be enhanced or reduced. It depends. Okay, so that is the effect that I am trying to talk about under this. Okay, nuclear overhazard effect is essentially the modification of the resonance line, resonance signal intensity of a nucleus, which is in the vicinity of the other nucleus. By saturating the other nucleus resonance, which is in the vicinity. So that's the nuclear overhazard effect. Okay, and these effects are very small; they are not very high. But then this will help us to determine the molecular structure. Especially this has become a great tool of importance to determine the three-dimensional structure of a protein. Okay, so that is very, very important technique, protein structure solving. Even now, it is a very much appreciated technique, because protein structure is something that is very complicated, very big. You have a lot of aliphatic chains through peptide bond. They're connected, and then they form the primary, secondary, and tertiary structures, right? So all these structure information is very important to understand and to develop some of the drugs and etc. So molecular structure determination is the primary thing in any of the drug development, right? So therefore, in that respect, the protein structure solving itself, it's a great importance. And in fact, several papers are given. If you recall the Uttarik, I mentioned that a couple of scientists' names who really were given awarded the Nobel Prize for the development or in and around the nuclear magnetic resonance. Uttarik is a person that he determined first time. I forgot the protein structure. He determined the protein structure after that one. And then using these two-dimensional technique. Okay, using these two-dimensional technique and two-dimensional techniques, and there are several things out there, and we'll discuss tomorrow further details, but then this is one of the principles used in two-dimensional NMR. And then I already given this, and I don't need this. That basically the modification of one nucleus resonance by saturating the other nucleus. Other nucleus is referred to as the nuclear overhauser effect. So what I'm trying to say is that, okay, let's say I have there are two nucleus which are connected, which are very close by in the space, okay? And this effect, let me tell you, this effect is not through the bond, but rather it is through space, okay? This example, I'm trying to give a cartoon diagram here that the nuclear Overhazard effect is found between two nucleus which are close by in space, not through the bond, okay? Through the bond, if something is happening, that we already understood that, that is a spin-spin coupling. The spin of one nuclei, the orientation of one nucleus spin will basically translated through the bonds and then accordingly to the other nucleus, and then we, as a result, we see splitting. That is a different thing. Okay, this I'm saying that this nuclear Overhauser effect usually takes place through space. Okay, and through space, A and B protons are connected here, and then they interact. And as a result, when you saturate B signal, this B, this proton, this resonating frequency will be either enhanced or decreased. Okay, so if it is enhanced, we say it's a positive enhanced, positive NOE, and if it is decreased, then we say it is a negative NOE. Okay, and this phenomena can be seen in several molecules. Okay, but for a simple molecule like this is not of great importance because you don't find it really, you don't appreciate this technique in the case of small molecules, because small molecule structure is a bit easy. You just imagine that you have a several molecule, Taxol molecule, okay, which is referred to as the cancer drug, very powerful cancer drug, but very difficult to synthesize, which has several stereo asymmetric centers. Okay, such a molecule, stereochemistry, if you want to determine whether it is in the towards you, pointing towards you, or pointing backwards the plane of the molecule. If you want to determine, this is one of the techniques. Okay, of course, this is not one technique, but many other techniques are there. Okay, but why this is happening? Okay, why this enhancement or decrease is happening? Primarily because of the population transfer. I mean, the spins getting transferred as they are close by in the space. The spins getting transferred. The spins see one another, and then this transfer takes place. And this transfer, what we call technically, it is a relaxation process. Okay, the nuclear Overhauser effect is primarily seen because of the dipole-dipole interaction. When the dipole-dipoles are interacting, then the spin relaxation takes place, and therefore we see either signal enhancement or decrease, depending upon the population. Okay, if the population is enhanced, the number of population is enhanced, the ground state and the difference is enhancing, such a process will enhance the signal intensity. Suppose when the dipoles are basically interacting and the population difference is decreasing, then the resonance signal intensity will decrease. So either it can enhance or decrease depending upon the population difference. Anything can happen. But the origin of the NOE is essentially is the dipole-dipole interaction. And this dipole-dipole interaction, I think you may recall that I already explained in the previous lectures. In a normal case, we don't see the dipole-dipole interaction very prominent, especially when you are dealing with a single proton in a given molecule. And you don't see really too much of NOE. But if you are finding more than one nucleus, then this nuclear Overhauser effect is going to be much more prominent. Okay, that is point number one. The other point I want to stress upon is that when the dipoles are interacting, okay, when the dipole are interacting, and if you have only one type of proton is there, then usually what happens, the interaction, dipole-dipole interaction, normally, since we are recording the NMR spectrum in a solution phase, in one particular direction, the dipole-dipole interaction is more, and therefore we don't see much enhancement or decrease. But then the dipole-dipole interaction will be dominating the relaxation process, and therefore we will see in certain cases the signal in the population transfer from the ground state to the upper nuclear energy state, and then as a result the signal enhancement we will see. Okay, and to explain all these things, I'm just taking one example, and this can be explained in many ways, this concept, but I'm trying to take one example. And what I'm trying to say so far is this. Okay, I have a AX spin system. I hope that you are following what is A and AX system. AX system is a spin system according to the Popel notation that A and X are according to the alphabet, they are far well separated letters. That means their resonant lines are well separated. Okay, in the NMR spectrum, the resonant lines are well separated as compared to the coupling constants. That is the meaning. So, what I'm trying to say is that nuclear Overhauser effect is nothing but, you have, okay, you can just concentrate here. The A is one resonating signal, X is one resonating signal, is giving. Now, in the nuclear Overhauser effect, what is done? That one of the signal, nuclei signal, will be saturated, will kept under saturation. What do you mean by saturation? This saturation process I have already explained. You just think of any nuclei, half spin nuclei. It will have a alpha state and beta state. Okay, and then in the case of a decoupler, explanation of the decoupling technique, I have explained this. But then again, I'm giving the same explanation. There is basically, you have a half spin nuclei and it has a two energy stage, alpha and beta state. Now, in the saturation process, what we do that the population difference we will make it zero. Therefore, there is no transition either from alpha to beta or beta to alpha. Okay, usually typically the alpha state is more populated and beta state is less populated because that is the excited state. And by the method of saturation, what you do that there is a decoupler. We use a decoupler. This decoupler is kept on throughout the experiment. If the decoupler frequency is kept on throughout the experiment, whose frequency is matching with the difference in between this alpha and beta, then what happens? Okay, initially the nuclei is in the alpha state, it will go to beta state, but it will not stay in the beta state. It will come back. It will not stay in the ground state. So it will shuttle between these two nuclear energy state. Therefore, in a given point of time, the population in the ground state and upper state, the molecule sees the difference is zero. Almost the equal, both the states are equally populated. If the states are equally populated, then we can't see a transition, right? We can't see any transition. That is what we call it as a saturation. So using that method, one of the signal intensity, okay, so you can set the decoupler whose frequency is matching with that, and then you can make it saturation. So saturation means that basically the transition, there is no transition, and as a result you will get a zero. So you don't get any signal from that particular thing. So if X is saturated, then what I'm trying to explain to you is that the NOE, according to NOE, if X is saturated, this signal intensity either will enhance or decrease. That is what I'm trying to say so far. So there is nothing. Okay, sir, why you are saying yes? Okay, no problem. You can just saturate A. Okay, where A is resonating in the delta scale, you know very well. Okay, this is start from 0, and then it is going in the case of proton, it is going to up to 12 or 15. So you know where exactly A is resonating. With that frequency, you just set the decoupler frequency, which is matching with the A resonating signal. Therefore, under that such in those cases, in that case, it's a signal intensity. The X signal intensity either will go up or go down. It depends upon the couple of factors. So what kind of dipole interaction is taking place, and what is the chemical environment, what is the solvent is being used, how fast the molecules are moving in the medium. So there are several factors out there. Okay, so that is what the NOE brief explanation. And then NOE, to explain, let me take the same AX example, and then you can arrive at, if it is a AX system, that we can arrive at 4 spin states, right? Alpha, alpha, beta, beta, alpha, beta, 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 alpha. So these are the four, spin state that we can deduce from the AX spin system. Why I'm writing this spin system? Because they are coupling. Because through space they are interacting. Interaction means that they are basically coupling. So the dipole of the A, dipole of X, both basically interacting. Therefore, they will lead to different spin energy states. It's not one spin energy state, but then they will lead to 4 spin energy states, and those spin states are shown here. And alpha, a transition, a transition from alpha alpha to beta beta. So this transition, okay, this transition is one transition that we can expect. And alpha beta to beta alpha, this is one type of transition. Okay, vice versa, either alpha beta to beta alpha, beta alpha to alpha beta. So this is one type of transition. Similarly, we can also expect alpha alpha to alpha beta, alpha alpha to beta alpha, beta alpha to alpha. So these are the different transitions are possible between the two dipoles upon the interaction of these dipoles, okay, separate individual dipoles. So in the case of NOE, what exactly is happening? So the dipoles are basically interacting, and they are transferring their spin systems from one spin energy state to the other spin energy state. Okay, there is a polarization transfer is happening. Spin polarization transfer is happening between these system. Therefore, we see either enhance or decrease. And why we see enhance, why we will not see enhancement, that we will go systematically to understand. Before that, let me tell you, and when you have these 4 spin energy state, and when we have these many transitions, and each transition, what we call it as a, for each transition there will be a probability, right? For each transition, according to the quantum mechanics, that you can have a transition probability, and these transition probabilities are shown here, that the omega 0 is the zero quantum probability. What is omega 0? Omega 0 is nothing but the single quantum transition, zero quantum transition. So this is the transition, alpha beta to beta alpha, or beta alpha to alpha beta. So if a, what is this alpha and what is beta? Please remember that this is the, note down here that the AX, okay, I'm showing in this case, left hand side, the blue color indicates the spin of the alpha A, and one nuclear. A means one nuclear, okay, and the other one, the red, indicates the spin of the other nuclear, X nuclear. Okay, so these spins are basically through space they are interacting. Now, if the interaction is taking place alpha beta to beta alpha, so this we call it as a zero transition. Okay, so what is happening exactly? You see that A is transferring its spin to, suppose this is the transition we are talking about. Alpha is getting to beta, and beta is getting to alpha. While alpha is transferring its spin to beta, while A spin is transferring its spin, changing its spin alpha to beta, X transition, X spin also changing beta to alpha. Okay, that is what I mean. Now, so the net effect is zero, right? The net effect is zero. Both are changing. I mean, both spins are getting changed. Therefore, this is, we call it as a zero transition probability. This transition, what we call it as a zero transition probability. You just look at here. You just look at here, and then you have a beta alpha, and then beta beta state. So what about this transition? This transition, you just look at here. Beta spin state remain the same, while the alpha, sorry, A spin state remains the same, but X spin state is getting changed. Initially it is alpha, but then here the transition, X spin state is changing to beta. What about this? Here A spin is changing alpha to beta, while the B spin is remain the same. Okay, when we talk about this, you can follow the same thing, that A spin is alpha, is changing to alpha to beta, but the X spin remain alpha, remain same, right? And in this case, the X transition is changing, while the A transition, A spin state is remain the same. So therefore, we call only one in all these things. This is 1, 2, 3, 4. So all these 4 transition, same thing is happening. One of the nuclei, either A or X, their spin state is changing, either to alpha to beta or beta to alpha. Something is happening. Therefore, since only one of the nuclei is changing, therefore we call it as a single transition probability. Single probability, transition probability. In the previous case, both are changing. I mean, while alpha is changing, while A is changing to alpha, changing, and beta is X is also changing. The other nuclei, both nuclei spins are getting transferred. Therefore, it is called as a zero. What about this one? Just look at here, either from alpha alpha to beta beta, or beta to alpha alpha, either from ground state to the excited state or excited to the ground state. In both the cases, and in both the spins are getting changed, right? This transition, both the nuclei, alpha is changing, sorry, A spin state is changing from alpha to beta, and in this case, okay, and X spin state is going from alpha to beta. Suppose if you talk about uh, from the from the transition from beta beta to beta, beta beta to alpha alpha state, then in that case, initially the A spin state is beta, then it is getting to alpha. Okay, it is beta, and then its spin state is getting to alpha. Okay, beta to 1. So both are changing. Therefore, we call it as a double probable, double quantum transition, double quantum transition. So the 2 nuclei are involved. Okay, so that is the terminology. You please remember these things, because these are important to understand why uh, the enhancement or decrease is happening. Either the enhancement or decrease is happening mainly because of this relaxation process, and certain cases this either double quantum transition will be more dominated than the single and the zero quantum transition relaxation process, and in some of the cases the W1 will be dominating, in some of the cases W0 will be dominating. It depends upon the thing. Okay, so the dipoles are interacting with each other through space. Therefore, the spins are getting exchanged from one nucleus to the other nucleus. Okay, how they are exchanging? There are 3 ways they are exchanging. Zero quantum probability, both spins are changing. Okay, the net is 0. Okay, the net effect is basically zero, both alpha to beta. The other one is alpha beta to alpha, like that. So zero quantum probability. So that is one way of relaxation. Okay, the spins are changing, exchanging their spins, and they are relaxing back, right? So that we call it, that process we call it as a relaxation process. And for that relaxation process, there is a probability. That probability are represented with the omegas. Okay, and the another thing is, like, one of the nuclei can change. One of the nuclear spin can relax back to another one. Alpha can go, A spin can go to alpha to beta, or the X spin can go alpha to beta. Okay, so anything can happen. One of the nuclei will change. That is the single. That is one type of relaxation process. So that we call it a single transition relaxation process. And then there is a probability for that. Then that is W omega 1. Similarly, omega 2. Okay, I think this is the explanation which I have given. So let's take one example okay, I mentioned, let's say that the omega 1 is the relaxation process that is taking place. Let's say, for example, the omega 1 is the relaxation process that is taking place for some reasons in the given system. Then what exactly happens? Okay, so this is the pictorial cartoon diagram representation, which gives you if omega 1 is the dominating the relaxation process, then how the population difference getting affected and how the signals are affected. So it is shown in this picture. So let us go by point by point. So let's say here I have shown here this is the A, this is the X. So on the left hand side, it's the blue color indicates the A spin, one nuclei, the red indicates the other nuclei. Okay, and the alpha and beta, these alpha and beta represent A, and this alpha and beta represent the B. Okay, so as usual, there is a population difference. Okay, there will be always there is a population difference from the ground nuclear energy state to the excited nuclear energy state. Therefore, you will see a corresponding NMR signal when you record it. Okay, so these signals you can see here. In this case, just to give you some flavors, that the population difference is shown as a 4. Okay, one line, there are 6 lines on the 6 population on the alpha state, and then 2 lines in the beta state, and the difference is 4, and accordingly you will get it, the signal. Similarly, X also, you have 6 population in the ground and 2 population in the excited beta state of the X spin state. Therefore, you will get so since the population difference in both cases is 4, you will get the equal intense NMR signals. Okay, that is the usual one. But in the NMR, the NYE experiment, what we do exactly, we saturate one of the nuclei. Let's say for the sake of understanding, let us, this X is radiated with a double frequency resonator. Therefore, it gets saturated. X is saturated. If X is saturated, there won't be any population difference, and then it will be 0. Therefore, we don't see any transition. Okay, we don't see any transition. Therefore, it will be as a signal will be not seen. Okay, this is the example of that. Okay, so X A we are not changing anything. Therefore, still there is a population difference of 4. Then corresponding signal can be seen. But X, okay, this is the condition under which X is saturated. That means the saturation is a process of making equal population in the ground and excited state. Therefore, there won't be any transition, and then we don't see any signal for that, and it is shown here just like with a small dot. Okay, I'm sure that you are following what I'm saying. And then the next process, what we do, we are saying that the omega 1 is the dominating process. That is the case we have taken. If omega 1 is a dominating process, what exactly happens? Omega 1 means what it is exactly. Omega 1 means one of the nuclei will change. One of the nuclei will change its spin, right? One of the nuclei will change its spin. Okay. So in this case, what I'm saying that what I'm taking an example that the X1, X spin state will change from alpha to beta to alpha or beta to alpha. Anything can be taken. That's not the issue. Okay. Either this way or that way you can move. But still the difference is same. Okay. So in this case, we just see beta of the X actually is transferring to alpha. This is one relaxation process, right? Beta is getting transferred to alpha. Which one? Which beta? The beta of the X spin. Earlier, just previously, since we saturated, there is a equal population. Then there is equal population. There are 4 population beta state, and one of the beta will come to the ground state. Okay. Now what you see here, what you see here, and there will be 5 in the ground alpha state of X, but here it's only 3. So here now it is 5, and this is 3. Therefore, the difference is 2, and then there is an enhancement in the signal. Okay. So you can basically continue this discussion. How long you can continue? I mean, next one again, another beta of the X, and another one can transfer to the alpha. The population difference will be going to 4. Okay, the population difference is going to be 4, right? And then it will keep on changing. Then it will keep on changing. So in this case, what exactly is happening is that we don't see any kind of net signal, either enhancement or decrease. Okay, I repeat the process. Here you can see here, initially the signal intensity is this much. Okay, and the X signal is this much. Okay, now what we are saying, because of this single quantum relaxation process, the X nucleus spin is getting changed from beta to alpha. Therefore, it will continue this process. I have stopped here, but then the similar thing you can continue here. One of the things will come here. Then in that case, the signal intensity goes up, because this will become 4. Okay, this will become 4. Then therefore it will become the equal intensity as the AI signal. And in this case, as you can notice here, you irradiated one of the nuclei, and then slowly the intensity of that one actually comes back to the original state. Okay, original state means this is the intensity. Okay, so it will come back to the same intensity as this one. Therefore, in this particular case, suppose if the single quantum transition is the only dominated process, then we don't see any signal enhancement or decrease. Why? Because the population difference actually comes back to the same situation. Okay, only one nucleus is involved, and then what we get is essentially the same signal intensity as before the irradiate. Okay, but if you come across the other cases, like if omega 0 is taking place, or omega 2 is taking place. What is omega 0? Omega 0 is the zero quantum transition, probability, and omega 2 is the double quantum transition probability. Okay, so those things, in those cases, we will say either positive NOE or negative NOE. Again, I will take the same example, AX spin system. I will try to explain. Suppose if omega 0 is the dominating process. What is exactly omega 0? You please recall, omega 0, both nuclei will be changing their spins. Both nuclei will be changing their spins. That is the omega 0. Okay, now we just try to understand. I did not show the saturation concept, but then I started from the saturation, because since we already understand that thing, it is not explained here. So initially we saturated the X nuclei. Okay, now you start applying the omega 0. What is omega 0? Both will be exchanging their spins. Both will be transferring their spin through dipolar interaction. So while X spin, the beta spin of X is coming to alpha, alpha spin of the A is getting beta. So that is the way it is. You remember that it is nothing but the alpha beta to beta alpha. Okay, that is the center. You have alpha state, alpha here, beta beta. Then in between you have two states are there, that alpha beta and then beta alpha. Okay, so the transition between these two lines, what we call it as the zero quantum transition, and it's a probability zero quantum transition. That is the relaxation process we are discussing. So both are getting changed here, the spin. Therefore, what you see is that there is a substantial decrease in the original intensity of the A signal. A signal is what? A signal is the one. We did not irradiate this one. Please remember that. We only irradiated this one. we only iterated x1, and then as a result, this probability, the difference become population difference becomes 0, and then it is that. But when the the zero, when this relaxation process is happening, then what happens? Okay, so uh, alpha is going to beta. Okay, the beta of x is coming to alpha. Therefore, accordingly, you change the population difference. As you can notice here, the population of this one actually decreases. Okay, initially it was 4, then it is decreased. Again, you apply the one more time. Again, it will accordingly. You will see that initially it is this much intensity, but now it is double, half of the initial way. Where resonance signal is initially it is this much, then when you move one, when the population difference becomes 2, then naturally the signal intensity reduces. And if you keep on moving the arrows, from alpha to beta of the A, again the population difference further decreases, and then it will lead to uh, the signal A intensity will be almost 0. It will be seen at the bottom. You don't see anything. Therefore, what exactly is happening when you try to compare with the original situation? Originally, the A signal is this much. Okay, so this much, but then after saturation, it will be almost 0. So therefore, it is called as a negative NOE. This particular thing, what we call it as a negative NOE. Then what about this one? The right side one is the positive NOE. In this case, as you can notice here, the positive NOE means that saturation. Again, I started from the saturation. I have when I saturate X nuclei, and there is a 0 population difference, and A signal, the population difference is 4. Okay, and when I apply the double quantum relaxation process, then both the spins, okay, you have to put both either top to bottom or bottom to top, okay, both arrows. In this case, okay, initially there is a 2 are there, and then one after the 2 will come down, okay. In the case of X nuclei, it's 4 or 4, and then it becomes 3, and it becomes 5 here. In the case of A, it becomes 6 because one of the 2 came down, so the population difference is enhanced. The difference increased, therefore the signal intensity will enhance from the original signal intensity. Okay, please note down that we are playing with the saturation of the X nuclei. Therefore, we only have to look at the other nuclei signal intensity, not the X nuclei, because that is immaterial. Okay, you can do the other way. In that case, you can look at the signal of the X1. So the nucleus which we are saturating, we should not look at its intensity. Naturally, it will either fluctuate. That is not of our importance. What is important is that when you saturate the one, the other one intensity get basically enhanced or decreased. That is something that we have to always keep in mind. Okay, so in the case of the double quantum transition process, the population difference actually enhances, therefore the signal intensity increases. So this what we call it as a the positive NOE. Okay, so positive NOE means that the as compared to the original signal intensity of A, the after population, after applying the, after it has relaxed back using the double quantum relaxation process, then its intensity basically enhanced. Therefore, it is a positive, right? So this uh, uh, we can actually calculate the enhancement factor based on which basically we can arrive at a couple of points, and then we can determine in the molecular structure also. Okay, so that's the explanation about the NOE. NOE is essentially is happening because of the dipole-dipole interaction. As a result, the signal enhancement or decrease will happen. That's the broad idea of NOE, and this is happening because of the molecular motion, and the molecular motion basically is governed by several factors. One of the factors is the correlation time of the molecule. Okay, one of the factor that affects the NOE is the correlation time. So depending upon the correlation time, one of the process will be dominating while the other will be suppressing. Okay, the best example is that, in the case of if the molecule is slowly moving. Yeah, if the molecular motion is uh, very slow in a given medium while recording the spectrum. Okay, in that case, the W0, that is a zero quantum probability, will be a dominating process as compared to the other one. Okay, but if the molecular motion is much faster, then the W2, omega 2, sorry, not W, omega 2, the double quantum relaxation process will be very much dominated. Okay, but then when a molecular motion will be faster, and then when it will be slower. Let's say if my molecule is a small molecule, then there is a high chance that its molecular motion will be high, right? Because it is in the liquid medium, it basically moves fastly because of its a small size. Suppose if the molecule is basically if the molecule is very bigger, it can't move very fastly in the medium, right? In that case, omega zero, the relaxation process, the zero quantum relaxation process will be high. And what will happen? And so similarly, you can also look at the other aspect, like the viscosity of the medium. Viscosity of the medium is one thing that actually determines the molecular motion. Okay, suppose if you are putting a molecule, same molecule, in a viscous medium and in a less viscous medium, its molecular motion will be very high in the less viscous medium, right? So in that situation, accordingly, the omega 0 or omega 2 will be dominating, right? That is one thing. Similarly, the temperature of the medium either can be enhanced or decreased, such that one of the process can be made it very fast. Suppose if you lower the temperature, then omega 0, that means omega 0 process will be high. That means the negative NYU will be absorbing. Suppose if if the temperature of the medium is enhanced. Okay, now most of the NMR spectrometers comes with the Peltier. That means you can basically carry out the experiment at different temperature, and then if you enhance the temperature, if you increase the temperature of the medium, therefore in that case the molecular motions are very fast, and then W2 becomes very prominent, and then accordingly that we will always observe the positive NOE. So the molecular motion is the key factor, and then the dipolar interaction is the another factor, and the NOE enhancement or the enhancement factor can be obtained, okay, by using this formula. Okay, the enhancement factor eta is equal to IA minus IA naught by IA naught. What is IA? Before and after applying the secondary, so before and after applying the saturating pulse. That is the thing. So after saturating, okay, if this factor, if this is high, I mean if this signal intensity is high, then obviously we will see a positive NOI. Okay, and then as compared to the before applying. Okay, so this is the simple formula that anybody can just take before and after applying the difference between the two signal intensities, and then we can calculate the factors, and accordingly can say it is a positive NOE or negative NOE. Okay, and then the enhancement factor can be anywhere between -1 to 0.5. Okay, -1 to 0.5. Anywhere it can be depending upon the situation. And for photons, this is the situation, but for the heteronuclear thing, it will be different. Okay, if both A and X are, I just explained with the half-spin nuclei, and if both are basically protons, same type of nuclei, then this is the observation. So -1 to, it will vary from -1 to 0.5, anywhere it will vary. And then the NOE basically depends upon the gyromagnetic ratio of the nuclei which we are dealing with. Okay, and the relation is this. So n is equal to gamma x by 2 gamma a naught. That is the relation between the enhancement factor and the gyromagnetic ratios. Okay. And then what else I have? I think these are all already covered. Yeah. And one of the most important point I just missed out, but anyway, it is the point to explain it. I think this is the right time to explain this. The NOE is the through space interaction mechanism. It is happening because of the dipole-dipole interaction through space. Now, when I said is space, there should be limit. Okay, whether if you keep them very far apart, will they see? Do we see NOE? No. So there is a limit for that. The NOE, to observe NOE between any two nuclei which are close by in the vicinity, their difference, the distance must be within 5 angstroms. So that is very, very, very essential point and important point. Keep in mind. If the distance between the two nuclei is more than 5 angstroms, this dipolar interaction basically not seen, and the relaxation not seen, and then we don't see any kind of signal enhancement or decrease. Okay, why? Because through space and through bond, both interactions are they follow different mechanism, different chemical, different formulas. If you remember correctly, if it is a through bond, it is a 1 over r cube is the interaction. If r is increasing, cube root of r 1 over r cube it will be. But through space, it is 1 over r power 6. If it is a through space, the interaction, dipole-dipoles are interaction, and what is interaction if you want to say, if then it is related with the 1 over r cube, r to the power 6, if it is through space. Therefore, accordingly, the NOE will be seen, and then that is actually, in fact, useful phenomena to arrive at certain numbers. In fact, this is the major application of NOE in the 2D NMR spectroscopy. What it is done, since it is r to the power 6 difference, r to the power 1 over r power 6 is the relation between the distance. The enhancement factor eta is related with the enhancement factor, right? Is related with the distance. What is the distance? Since they are through space, therefore it is 1 over r cube or r to the power 6 difference. Therefore, which means is that basically you can actually calculate the distance between the two nuclei. By doing the NOE experiment, you can calculate the distance. Why? Because NOE is directly, this is the point I was talking about. NOE is directly proportional to, indirectly proportional to 1 over r to the power r cube or r to the power 6, right? This factor, what is that factor? This factor I was talking about. This is a factor that we can calculate simply by doing the NOE experiment. We can calculate this. But this eta is basically it basically depends upon r to the power minus r to the power 6, right? And if you know this, if you are able to calculate this from the NMR spectroscopy, then that means you will be able to calculate the distance r, right? This r is known. R is known from the NOE experiment. If r is known, then that means you will be able to say in the through space there are two nuclei, they are connected, and therefore connected, and the distance between them is this much. How you can calculate? Because they are related with the distance. Okay, so this is a very useful tool for the 2D NMR spectroscopies. They use this information. And they store it. It's not one type of experiment they do and then solve the 2D NMR spectrum of a protein or any other molecule, but there are several other experiment of this kind is done continuously and systematically to find out all the R's. Okay, how through space different. Okay, now you are taking there is through space two things are connected, one proton, and there is one proton, number one. So how, what is the distance they calculate, and then there is another proton, how they are connected, and these two are how they are connected. So this information can be deduced by carrying out the NMR experiment, several series of. So that is the main job of these 2D NMR spectroscopy persons, and then they finally map all the distances. Okay, and then they will basically give the molecular structure of the protein, or in general it is a complex molecule. That is very, very important. That is very, very important and very, very useful. Why? Because let's say the complementary technique we have, ultimate complementary technique we have is the X-ray diffraction technique to determine, to illustrate the molecular structure of the molecule. You know that the X-ray diffraction technique is the one, especially the single crystal X-ray diffraction technique. It gives you precisely the bond length, bond angle, how they are arranged in the space, and are there any solvent molecules, what are the interactions, everything it gives. But then the problem with the X-ray diffraction technique is it is a solid state structure. It is a solid state structure. But when you look at, when you're dealing with the protein molecular structure, it is present in our body. For example, you take any proteins, very important proteins of our body, and they are present in a solution phase in cells. They are present in cells in a solution phase. The protein structure in cells is not exactly same as the protein structure of the same protein structure in the solid phase, because of the the solution. When you keep it, you have a lot of the moments and a lot of other translational movement and vibrational, everything happens. But in the solid phase, the molecular structure has a limitations. Certain molecular motions are frozen. Therefore, that molecular structure is correct only in the solid, but then that you can't take it and then apply and try to knock with some drug molecule and say whether this is suitable or not. That is not possible. But in the case of NMR, the beauty of this NMR technique is that it gives you the molecular structure information in the solution phase. Why? Because the NMR technique itself we are carrying out in the solution phase, right? Therefore, any medium, usually the chloroform or any deuterated solvent, most of the deuterated solvents are used, and therefore the molecule is present in a solution phase. That means the molecule is present more or less similar to that of the chemical environment of the protein present or complex molecule present in that particular body, human body or any other organism. So this is where the NMR technique is different from the X-ray diffraction technique. Okay, because this is also in one way, as the molecule size get bigger and bigger, X-ray diffraction techniques we can't use because we can't really grow a single crystal. Only then, if you have a single crystal, that single crystal can be used to determine the molecular structure. But as the molecular size enhances, then it becomes so complex. The solubility becomes so complex, and we can't really grow a single crystal. But if you can grow single crystal, but the single crystal diffractometer gives the structure. Okay, that is there. But in the case of proteins, it is very difficult to grow the single crystal. So that the difficulty which is there with the single crystal analysis or the X-ray diffraction analysis of the proteins is overcome with the NMR techniques. Okay, that is one thing. The second point is that it gives you direct solution phase molecular structure. So that is, anyway, it is highly appreciated because the molecule present, that is also protein is present in the similar structure with that almost similar structure with that of the human cells or any organism cells. So that is the beauty of the NMR technique. Okay, now in a routine experiments where exactly we use NOE technique is something that I'm going to explain to you, because this is something will be useful for us. Now you can see here that stereochemistry, whether it is the Z configuration or E configuration, that is of our interest, routine chemistry. Whether it is Z or E, how do we determine? This is the way that, what you can do. If you try to record the NOE enhancement factor from this molecule, both the cis and trans isomers, actually, when they try to calculate, when they try to do this thing, then they have seen 31% enhancement, this proton signal, right? Whereas if the proton is there, then you don't see any kind of enhancement. Okay, you can't see any enhancement. If you try to see the NOE enhancement of this proton and this proton, since they are very close by, you will see a nice NOE enhancement up to 31%, right? On the other hand, suppose if this is present, in this configuration, then you don't see any signal enhancement. Therefore, we say both are trans. Okay, both are trans. So that means that allows you to basically determine the stereochemistry of that particular thing, right? Similarly, this is another example. Okay, assignment of stereochemistry is the major important thing. Okay, the same thing. There is a methyl group, this carbohydrate molecule. There is a methyl group here, and then that is interacting. Since they are both are nearby, you can see the signal enhancement. But if you see the other configuration, axial and you have the axial and equatorial combination. So when you try to calculate the NOE enhancement from this methyl proton and this one, you don't see it, because both are very far. If both the partners are very far, that means more than 5 angstrom, then you don't see NOE thing. Therefore, it doesn't give any enhancement, a signal enhancement or decreasement. Therefore, we can conclude that accordingly, whether it is an axial proton or equatorial proton. Similar, another example of this kind. So there are several examples of our interest. This is what I was talking about. For a chemist, this is what is important. For a chemist, assigning the stereochemistry is more important, and in that respect, this NOE is really helpful technique. Okay, I think this is what I just wanted to discuss for today. And if you have any questions or queries, probably we can discuss. Otherwise, we can stop here.